Okay, good morning, students. We are discussing about the flip-flops, and in the previous class, we have discussed about SR flip-flop and D flip-flop. On your screen, you can see the D flip-flop. I have shown two different block diagrams of the D flip-flops. So one is the rising edge trigger D flip-flop. Another one is falling edge trigger D flip-flop. So there you can see the difference between the rising edge and falling edge, how it is indicated. If you don't show bubble to the clock, it is called as rising edge triggered flip-flop. And if you add a bubble to the clock, it becomes a falling edge or negative edge triggered D flip-flop. So after studying these two flip-flops, that is SR flip-flop and D flip-flop, now we are going to study about the JK flip-flop. Right. So we know that in SR flip-flop there are two inputs, S and R, and we have seen depending on the values of S and R, and when clock is applied, we will get the output that is depending on the values of S and R. If S and R both are 0, 0, there will not be any change in the output. The output remains same. Similarly, when S is equal to 0 and R equal to 1, it resets the flip-flop, which indicates Q equal to 0 and Q bar equal to 1. And when S is equal to 1 and R equal to 0, sets the flip-flop, and we get Q output as 1 and Q bar will be 0. And when both the inputs are 1, 1, that is S is equal to 1, R equal to 1, then the output of the flip-flop will be indeterminate. That is, that state is called as the forbidden state or indeterminate state of the SR flip-flop. Right. Then we have seen the D flip-flop, how we can construct a D flip-flop from the SR flip-flop. If you connect D to the S input and complement of D is connected to the R input, then the SR flip-flop can be converted to D flip-flop. So wherein we have a single input D and the output Q will be equal to D. That is, if D is 0, we'll get Q equal to 0, and if D is 1, we'll get Q equal to 1. And all these state changes in any of the flip-flop takes place only when there is a clock applied. And if there is no clock, then the flip-flop remains in the previous state. That is, flip-flop will hold the value unless and until the clock is applied, and based on the input values, the flip-flop may remain in the previous state or it may go to the different state. So after discussing these two different types of flip-flops, today we'll discuss the remaining two flip-flops, that is JK flip-flop and what is called as T flip-flop. So first we'll try to discuss about what is called as the JK flip-flop. I hope the board is visible for you people. Is it visible? Is the board visible?
Yes, sir. Yes, sir.
So this is what is there on the board, the last flip-flop which we have discussed, called the D flip-flop. Now we'll discuss JK flip-flop, one of the important flip-flop that we are going to discuss now. So the important drawback of SR flip-flop is that when both the inputs of the SR flip-flop are 1, 1, the output is indeterminate or forbidden. So to overcome that drawback of the SR flip-flop, we are going for the JK flip-flop, and in JK flip-flop, this indeterminate state of SR flip-flop also is used, or it can be considered. So all the four inputs can be considered in JK flip-flop. So we'll see what exactly the JK flip-flop is and how it overcomes the drawback of SR flip-flop, and what are the different states that the JK flip-flop can work depending on the input. So here JK flip-flop, like SR flip-flop, has two inputs and the two outputs which are complement of each other. Like in SR flip-flop, the inputs are denoted by S and R, whereas in JK flip-flop, the inputs are denoted by what? J and K. So we'll see what is this JK flip-flop now. So the condition 1, S equal to 1, R equal to 1, we have to eliminate here in this particular flip-flop called JK flip-flop. So what I do is, I will draw the SR flip-flop again. All of you know the SR flip-flop using NAND gate, how it can be drawn. How many NAND gates you have to use to draw the SR flip-flop? Yes? Totally how many NAND gates you have to use to draw the SR flip-flop? There are no answers. So it is better not to ask any question for you people. How many NAND gates you have to use in SR flip-flop? Yeah?
4.
4 NAND gates. Good, at least one response I got. So you know that how it should be drawn. First is SR latch using NAND gate, to cross-coupled NAND gates you have to draw. Right. This is a NAND latch. Now to this we'll add 2 more NAND gate. Here we'll give the clock, and then we have these 2 inputs. Right. And we denote these 2 inputs by S and R. This is a logic diagram of what? SR flip-flop. Now how we can convert this SR flip-flop to JK flip-flop? The first thing is, you have to remove S and R inputs and denote these 2 inputs by what now? J and K. Just by changing S to J and R to K, it will not become JK flip-flop. Right? So what is the important change that you need to do here to eliminate that forbidden state which is present in the SR flip-flop? So to eliminate the forbidden state of the SR flip-flop, what we need to do here is, we have to take the output Q, and connect it as a feedback to the lower NAND gate, and take Q bar and connect it to the upper NAND gate. This is the logic diagram of what? This is the logic diagram of JK flip-flop. I hope it is clear. What changes you need to do in SR flip-flop to get the JK flip-flop? Yes? Yes, Ritika? What changes you need to do in SR flip-flop to get the JK flip-flop? In fact, I have already drawn that diagram on the board. What changes I have done here? Yes? Are you there, Ritika?
Yes. Yes, sir.
What changes we need to do in the SR flip-flop to get the JK flip-flop? What changes I have done here? See what it shows. Right? Just now I have drawn the diagram. I have explained how SR flip-flop should be changed to JK flip-flop, but still you are not able to tell what are the changes you need to do in the SR flip-flop to get the JK flip-flop. Yes? What changes you need to do? Can anybody? Is there Rahul? Yes? Akanksha?
Yes, sir.
Yeah. What changes I have done in the SR flip-flop to get this JK flip-flop?
So we have to add 2 NAND gates J and K.
No, that was there in the SR flip-flop also. Basic diagram of the SR flip-flop, you know. In that SR flip-flop, what changes I have done to get the JK flip-flop?
The output of Q, we have to add it to the lower NAND gate of K.
Okay.
And output of Q bar, we have to add to the upper NAND gate.
Output of Q bar should be added to the upper NAND gate. So this feedback arrangement we have to make to eliminate that 1-1 condition which was there in the SR flip-flop, that is the forbidden condition. Again, you know that we are using NAND gate here. What are the properties of the NAND gate? you can write down the truth table of the NAND gate. What output you will get for 0 0 1 0 1 1 1 0 1 1 1 0. This is the truth table of what? This is the truth table of what?
NAND gate.
NAND gate. So we have to use this truth table of NAND gate to illustrate the working of JK flip-flop. So again, we will consider from this truth table we can see that 0 input at the NAND gate forces the output to 1 irrespective of the other inputs. If we have one of the input to the NAND gate as 1, we will not able to decide its output unless and until we know the other input. Now using this, we will try to explain the working of JK flip-flop. So I will consider the clock, then we have to write now J, K, right, Q. If you want, you can have Q bar also, and then you write the state. So whenever clock is not there, we'll see, and when we apply the clock, what will be the output? That's what we are going to check. So in the absence of the clock, what happens? Irrespective of J and K, or whatever may be the values, in the absence of the clock, Q remains Q only, Q bar remains Q bar, and that is no change. I need not explain this case. You can just try it on your own. I will be explaining now the remaining 4 cases. That is, when we apply the rising edge of the clock, first clock, second clock, third clock, what happens? And we'll take the values like 0 0, 0 1, 1 0, and 1 1. Right? So I will take the first case. Clock is applied, and I am giving J equal to 0 and K equal to 0. Right? So when you apply clock 1 and if J is 0, right? 0 input at the NAND gate forces its output to 1. This also become 1. And when we have 1 input to the NAND gate, we will not be knowing its output unless and until we know the other input. So if you assume Q equal to 0 and Q bar equal to 1, now this 0 will come here and it will make the output of this gate as 1, and this 1 and 1 will make it 0. That means when we apply clock and if we give J equal to 0, K equal to 0, if the initial state of the flip-flop is Q equal to 0, Q bar equal to 1, the next state also we are going to get the same. On the other hand, suppose if Q is 1 and Q bar is 0, and I have applied J equal to 0, K equal to 0. So again I will get 1 1 here. So this 0 will force this output to 1, and this 1 and 1 will make the output to 0. So if previously Q is 1, again we are getting 1. Previously Q is 0, again we are getting 0. That means when J is equal to 0 and K equal to 0 is applied, what will be the value of Q? Q remains Q. That means what is the previous value of Q? That only the Q will take, and Q bar remains Q. This state is also called as no change state. I hope it is clear. That is when we apply J equal to 0, K equal to 0. Now next case we will take when J 0 and K is equal to 1. Right. So if you consider J 0 and K equal to 1 now. Right. So the moment you see here 0, this will force the output to 1. Right. And here, if you assume that is 1 1 1, if you assume, then here all the 3 inputs are 1. This output will be 0. So this 0 will force the output to 1. This will force to 1, and this 1 and this 1 will give you 0. That means when you apply J equal to 0, K equal to 1, to this latch you are giving input as 1 0. And when the input as 1 0 to the latch, we are getting Q equal to 0, Q bar equal to 1, irrespective of previous value of Q. Previous value of Q may be anything. We are going to get Q equal to 0, Q bar equal to 1, and this state is called as the reset state of the latch. Fine. Now next, if I assume j equal to 1 and k equal to 0. This 0 will force the output to 1 and this will force to 0. 0 will force to 1, 1 and 1 will give you 0. That means when we apply j equal to 1, k equal to 0, what we are going to get is q equal to 1, q bar equal to 0, and this state is called as the set state of the latch, or set state of the flip-flop. Up to this point, JK flip-flop exactly behaves like your SR flip-flop. Now we'll see what is the important input combination, that is when both are 1 1. When both are 1 1 and clock is 1, we will not able to decide the output of these two gates. So for that we need to assume what is the previous state. Previous I will assume q equal to 0, q bar equal to 1. If I assume q equal to 0, q bar equal to 1, and if I given a clock and j1, k1, now this 0 will come here, 0 will force this output to what? Sorry, this 0 will come, it will force it to 1, and this 1 along with the remaining 1, it will give you output as 0. So 0 at the input force the output to 1, and this 1 and this 1 will give you output as 0. I hope all of you getting it. What I did is I explain once again. Clock is applied, j is 1, k is 1. So the two inputs to both the NAND gates are 1. We will not able to decide upon the outputs of this gate 3 and 4. If I take this as 1 and 2, output of the gate 3 and 4 we will not able to decide unless and until we know the previous state. So I am assuming previous state flip-flop q equal to 0, q bar equal to 1. So this 0 will come here now along with these two 1 and it will give you output as 1. And this 1 will come here along with these two 1 and it will give output as 0. Now here we have 0 as the input, so this output will become 1, and this one along with this 1 it gives us output as 0. Means when we apply j equal to 1, k equal to 1, if the previous output is q equal to 0, q bar equal to 1, the new output what we are getting is q equal to 1 and q bar equal to 0. That is, for 0 we have got 1 and here for 1 we have got 0. This is if we assume q equal to 0 and q bar equal to 1. On the other hand, if I assume q equal to 1 and q bar equal to 0, because this is possibility. There are two possibilities. Either q can be 0 or q can be 1. So if I assume q equal to 1 and q bar equal to 0, and again I give j equal to 1, k equal to 1. So what happens now? This 0 will come here and it forces the output to 1, and then this 1 will come here and it forces the output to 0. 0 will force the output to 1 and this one along with this one gives you output 0. So what we are getting, when we apply j equal to 1, k equal to 1, if the previous output is 1, we are getting 0, and q bar if it is 0, we are getting 1. So if you assume q equal to 0, you are getting 1, and if you assume q equal to 1, you are getting 0. That means what is the previous state? You are getting complement of that when you give j equal to 1, k equal to 1. Hence, for j1, k1, whatever is the value of q, complement of that you will take, and q bar will become complement of that means q, and this state of the flip-flop is called as what? What is this state is called as? What the state is called as? Yes?
Toggle.
Toggle state of the flip-flop, which is a very important property of the JK flip-flop. So obviously, JK flip-flop has eliminated the forbidden state of SR flip-flop, and that forbidden state itself is converted into toggle state. So toggle state means output will be complement of the previous input, previous output. previous value of the Q is 0, you will get new value as 1, and if the previous value is 1, you get the new output as 0. Hence, JK flip-flop eliminates what? The forbidden state of the SR flip-flop. And that is the operation of JK flip-flop for you. So, any doubts here? All of you understood it? If you have any doubts, you can ask. Yes? All of you understood this working of JK flip-flop? This is very important from your examination point of view. Yes? All of you understood it? Any doubts from anybody? Right. So, important advantage of JK flip-flop is eliminates the disadvantage of SR flip-flop. There is no forbidden state, and the forbidden state is converted here as the toggle state. So now, as a homework, you people try to draw the timing diagram for this. Consider some clock, take J and K inputs, random inputs, and you should try to draw what is the output Q for the input chosen at the rising edge of the clock. Okay. This is what is the JK flip-flop. But JK flip-flop suffers from one more small disadvantage, that is, when you apply J equal to 1, K equal to 1, sometimes the JK flip-flop may toggle more than once in a single clock cycle. When you give J equal to 1, K equal to 1, only at the rising edge it should toggle. Or if it is a falling edge flip-flop, it should toggle only at the falling edge. But since there are two edges in a single clock cycle, sometimes JK flip-flop may toggle more than once in a single clock cycle, and that condition of JK flip-flop toggling more than once in a single clock cycle is called as race around condition. Toggling more than once in a single clock cycle is called as race around condition, and to eliminate this race around condition in JK flip-flop, we go for what is called as master-slave arrangement of JK flip-flop. So master-slave arrangement of JK flip-flop is used so that one JK flip-flop is used as a master, another JK flip-flop is used as a slave, and we can get the two output Q and Q bar. So input J and K can be applied here, and the clock directly it will be given to the master flip-flop, and complement of the clock is given to what? The JK flip-flop. So this type of arrangement is called as master-slave JK flip-flop, wherein one JK flip-flop is used as a master, another JK flip-flop is used as a slave. The inputs are given to the master, output of the master are given to the slave. Direct clock is applied to the master JK flip-flop, and complement of the clock is applied to the slave JK flip-flop, and this arrangement is called as master-slave JK flip-flop, whose truth table remains same as that of the truth table written there, but it will eliminate what? The race around condition that we get in the JK flip-flop, right? So that is what is called as master-slave JK flip-flop. So how do we draw the diagram for the master-slave JK flip-flop? One master and slave we have to use, clock directly you have to give, and the complement of the clock you have to give it to the slave. So how we can draw the logic diagram for master-slave JK flip-flop using NAND gates only, right? This is the important question that you will get in almost every question paper. Explain the working of master-slave JK flip-flop. This is very important question, and you can expect this in your second CIE test too, right? And the same circuit which I am giving you here is there for your laboratory experiment also. Like realize master-slave JK flip-flop and verify its truth table. So what you need to do is, first you have to draw an SR flip-flop. Right. I'll tell you how you should draw the master-slave JK flip-flop. First you draw the SR flip-flop like this. For a time being, you forget about that flip-flop, right? SR flip-flop when less than R are replaced by J and K. So this is what is the SR flip-flop you have drawn. Draw one more SR flip-flop here. So you have to have another NAND gate, second NAND gate. This will be given here. This is given here. Then we can have a clock. We'll see what to give there. Then you should have next NAND gate. Here also you should have a NAND gate. Then this should be connected here. Sorry. This should be taken and connected here. Right. And then we have this is Q and this is Q bar. So what you need to do is now this Q bar output you have to connect to the upper NAND gate like this, and to the lower NAND gate you have to connect the Q. Take this Q, connect it to the lower NAND gate. This is what we have done. Right. Two cascading of two flip-flops we did. But what important change I have told is clock directly should be given, and the complemented clock you need to give it to the second flip-flop. So how do we give that complemented clock now? So take this original clock what you are having. I will take this. This I will give it to the NOT gate. Again I will use an AND only to construct the NOT gate. And then I will connect this. This is the circuit diagram for the master slave JK flip-flop. It looks very complicated, like there are so many gates we have drawn. But I told very simple way to draw this particular master slave JK flip-flop. How we should draw this? All of you can just concentrate here. First draw the latch. One latch you draw. You cross couple NAND gates 1 and 2. Then add 2 more NAND gates. You will get it like a normal SR flip-flop. Then draw another latch here, add 2 more NAND gates, you will get the second SR flip-flop. But we have to convert it to JK. So what you do is, take the final Q output, connect to the first flip-flop. Take the final Q bar output, connect to this upper NAND gate. Then give the clock to the first, that is master, complemented clock you give it to the slave, and this circuit is called as, what is called as? Master slave JK flip-flop constructed using NAND gates. So this will avoid the resurround condition in the flip-flop, and it functions exactly as per the truth table of the JK flip-flop. So hope all of you understood this. Any doubts here? All of you understood working of master slave JK flip-flop, or in particular JK flip-flop. The same working you have to write. What I explained for the single JK flip-flop, you have to explain the same operation with the help of this particular logic diagram, and this is called as master slave JK flip-flop. And I have told one JK flip-flop is used as a master, where clock is given directly, and the complemented clock is given to the another JK flip-flop, that is called as a slave flip-flop. So one is master flip-flop, another is slave flip-flop. Together we call it as a master slave JK flip-flop. Is that clear? So the important advantage of this JK flip-flop is it eliminates the forbidden state which is there in the SR flip-flop, and the forbidden state becomes, what it becomes here? The forbidden state becomes what is called as the toggle state in the JK flip-flop. Any doubts? All of you understood or no? Yes or no? If you are not understood, you can ask me what part you are not understood. I will explain it once again. Otherwise, if you understood, then we will discuss the last flip-flop, that is T flip-flop. Any doubts here? No doubts? Yes? I will tell at least yes or no, whether you understood it or not. Okay, fine. Saundarya and Sahana Kochargi says they understood. Fine, good. At least I got to reply. Thank you, Saundarya and Sahana. Okay, now quickly we'll discuss the last flip-flop, that is T flip-flop. Now, as the name itself indicates, unlike JK and SR flip-flop, T flip-flop has a single input, and that single input is denoted by T. Like D flip-flop also has a single input, T flip-flop also has a single input, and this T flip-flop is also called as toggle flip-flop. That means a part of JK flip-flop operation is implemented here, right? And this particular flip-flop is called as a T flip-flop, and this T flip-flop can be constructed using a JK flip-flop. So how we can construct it using JK flip-flop is a single input you connect, that is the T input, to both J and K. If you short J and K, if both J and K are shorted and connected to the single input, and if that single input is denoted by T, then this flip-flop is called as a T flip-flop. So it is similar to D. In D, what we did, both S and R we have connected to D, but not same. D is directly connected to S and D bar is connected to R. That's where we got the D flip-flop. Now, if we connect the same input to J and K, then this type of flip-flop is called as a T flip-flop, right? So what happens here? If T is 0 or T equal to 1, there are two possibilities now. So what happens when T is 0? What will be J and K input? When you give T equal to 0, both J and K becomes what? Yes? See here, I am giving T equal to 0. The moment you make T 0, what will be the value of J and K?
0.
0.
J and K become 0, 0. And we know that when J 0, K 0, what is the state of the JK flip-flop? When J is equal to 0, K equal to 0, JK flip-flop remains in what? Previous state or no change state.
No
So
change.
when T equal to 0, it implies J equal to K equal to 0 and Q remains in Q, and that state is called as no change state. Similarly, when we apply T equal to 1, we get both J equal to 1, K equal to 1. And what will be the output of the JK flip-flop if J equal to K equal to 1? What will
Toggle.
be? Toggle. That means Q becomes Q bar and it toggles. So what you can see from this, when T is 0, the flip-flop remains in no change state, and when T is 1, the flip-flop toggles. That's why this particular flip-flop is called as toggle flip-flop or a T flip-flop. So the truth table, you can write the same thing here. I can write a clock, then I can write T input, Q output, and the state. So when clock is 0, irrespective of T, Q remains Q, no change. When clock is applied and if T is 0, Q remains in Q, that is no change. And when T is 1, Q becomes Q bar, and this is called as the toggle state of the. So if clock is applied and T is 0, flip-flop remains in the no change state, and when T is 1, output will be complement of the Q output, so it toggles, and this particular flip-flop is called as a T flip-flop. So how we can draw the logic diagram for this T flip-flop using NAND gates? So we have to show 2 NAND gates here, then 2 more NAND gates. We will have Q bar, right? And then here I will have a clock. This is J and K, and the third input here should be from what? Q bar, and this should be from Q. This is what is JK flip-flop. I have drawn the JK flip-flop. So how you can convert this to T flip-flop? This is J, this is K. Both you short together, and instead of giving separate J and K, give single input T, and this is the logic diagram for the T flip-flop. Right? So I hope it is clear. All of you understood. what is the block diagram of a T flip-flop and how a T flip-flop functions and why it is called as a toggle flip-flop. Is that clear? All of you understood the workings of all the 4 flip-flops which we have studied so far? Yes?
Yes, sir.
All the 4 flip-flops we have discussed in detail. And that's what is here in the slide show. You can have. This is the edge trigger D flip-flop which we have discussed. Then the rising edge flip-flop. Right, these explanations already are given. Timing diagram is also given. Right, then the SR flip-flop. This master slave SR flip-flop also you can have. Like how we have drawn the master slave JK flip-flop, exactly in the same way we can have master slave SR flip-flop also. Right, and this is the master slave arrangement of the JK flip-flop. In fact, we have shown here SR latch, and to that we have added the AND gate. Instead of this, you can go for the diagram which I have given, wherein it is having 9 different NAND gates. Right, so that 9 NAND gates logic diagram, if you draw, you will get the master slave JK flip-flop. Right, and this is the truth table of the JK flip-flop. And this is what you have the lab experiment which you need to do in your laboratory. The diagram which I have given is here. The same diagram is drawn, and you have to verify the truth table by realizing the master slave JK flip-flop using NAND gates, and you can verify its truth table. Right, then this is there. Okay, this T flip-flop. Right. Then implementation of T flip-flop. Okay, so normally when we discuss about these flip-flops, apart from the 2 inputs, that is SR, JK, or single input D and T, flip-flops will come up with the additional inputs, and those additional inputs are called as preset and clear input. If the preset is active, initially the flip-flop output can be 1, and if the preset is not active, that is, if clear is active, initially the output of the flip-flop will be 0. So initially, if you want to set or reset a flip-flop, you can make use of these additional inputs of the flip-flop called clear and preset. Clear, if clear is active, the Q output of the flip-flop will be 0. The flip-flop may be anything, any kind of flip-flop if you use, and if you have the clear input, and if that clear input is active, Q output will be 0. Similarly, if you active preset input of the flip-flop, then the Q output of that particular flip-flop will be 1. When I say Q1, obviously Q bar will be 0, and when I say Q0, obviously Q bar will be 1. So these are the 2 additional inputs that you can see in all the kinds of flip-flops. That is called as clear input and the preset input. If clear input is active, Q will be 0, and if preset input is active, Q will be 1. So clear and preset inputs are the additional inputs that can be used, and that is what is shown here in this particular the slide, where we have taken D input, and you can see that whenever clear and preset are not, both should not be active simultaneously, because active low signal we have shown here, clear N and preset N, that is negative signal, means if it is 0 active, 1 not active, but you can't make both active simultaneously. That is like making clear and preset simultaneously active. You are asking it to set as well as reset at the same time. That is not allowed. So you should never make both clear and preset signal active at the same time. Only one should be active at any given time. Then irrespective of your input, whenever a clear is active, output Q will be 0. Irrespective of the input, when preset is active, Q will be 1. So those are the active like additional inputs we can have. Along with these clear and preset, we may have enable also. If you remove clock and put enable, normally it becomes like a latch. Right. So one more important part of the flip-flop I have left deliberately, which I will be covering in the next class, that is representation of the flip-flops by the logic equations called characteristic equation, and how state diagrams or state machines can be drawn for the flip-flops. So that is the important part, which we will be doing it in the next class, representation of the flip-flops using characteristic equation and using state diagrams. And then in the last part of this module, we have to discuss about the counters. So before we discuss about the counters, as I said, in the next class, I'll be dealing with the characteristic equation of the flip-flops. For each flip-flop, we have a characteristic equation. So what exactly you mean by a characteristic equation? A characteristic equation of a flip-flop is nothing but a logic equation that describes the next state of the flip-flop for the given input. So what will be the next state of the flip-flop? That can be easily obtained when we know the present state input, and that equation which is used to get the next state is called as the characteristic equation. And those characteristic equation we'll be discussing in the next class. Right? So before I close today's class, if you have any difficulties, doubts, you can ask. So in the next class, I'll be dealing with the characteristic equation and the state diagram or state machines or what is called as the state's representation of the flip-flop. We will be doing that in the next class, and that will be there for your second CI test. So the portion for second CI test is complete up to the flip-flop characteristic equation and the state diagrams. That means except counter part of this module, from where we have left the first CI test, from there till the flip-flops, the portion will be there for your second CI test, which is starting from 10th of December. Right? So before we close, if you have any doubts related to your subject or the test, anything, you can ask. Another 5 minutes time is there. If you have any queries, you can ask.